Hello everyone, I'm Rishun Wang from University of Bristol. Today I will be presenting my research on rotation equivariant networks and transformers for Zebrafish scale image registration. My presentation will cover four main aspects. First, about the research background. Zebrafish has been widely used in skeletal research. The scales are small bony units of the fish exoskeletal system and serves as an attractive model in the study of skeletal regeneration and bone formation. However, routine medium addition causes motion, changing the positions of fish scales over time, which presents challenges for observation. From example image pair, we can see that fish scales may be displayed randomly on the pair dish with arbitrary translation distances and rotation differences. Additionally, no ground truth exists for supervision, makes the evaluation metrics for registration unclear. We tested existing methods including traditional and deep learning-based approaches. In this test, only feature points within the fish scales were considered. The SIFT and ORB algorithm failed in registration. Similarly, pre-trained deep learning models relying on feature point matching had difficulties in rotation detection. This proves the necessity of creating a specific model for the fish scale image dataset. To address the challenges of fish scale registration, the following methods were employed. First, in network architecture, we decided to use detector-free methods that skip the process of specific feature point detection. Inspired by the YOLO model, we transformed the images into an array of features, each representing a local patch as a matching candidate. Furthermore, we used Siamese network architectures to extract features from moving and fixed images. Since rotation is crucial, we introduced rotation equivariant network based on general E2 equivariant stable CNNs as the backbone of the feature extraction modulars. We tested two feature extraction backbones, with and without an upsampling process. After that, a transformer-based modular was then applied to calculate the similarities between extracted features, yielding a multi-channel confidence map with the respective transformation parameters, which was then used to establish the transformation matrix. To train the network, we created an artificial dataset containing pairs of synthetic images together with transformation matrix and parameters. We manually cropped several fish scales out of the background using binary mask. Random transformation parameters were selected to create the moving images along with the mask. The images were reshaped and the grid was applied to filter matching candidate. Then this process was repeated for the fixed images. With predefined parameter sets, the corresponding candidates were determined and used to generate the matching map. The loss function consists of two parts, negative log likelihood for matching confidence map and smooth L1 loss for other independent parameters, including rotation angle, scaling, and coordinate compensation. For evaluation matrix, we used the dye similarity coefficient index and the complex wavelet structural similarity index, which extends the conventional structural similarity measurement to the complex wavelet domain. It is insensitive to small distortions and provides gradual variance values. We tested DICE and the CWS SIM index on 17 cropped fish scales for 3 types of transformation between the same and different objects. The results illustrated here proves its feasibility for continued distortion detection. However, we must ensure that rotation differences between targets are within 90 degrees. Moving to the result, we utilized the matching points and the calculated parameters to transform the moving images and closely assess local areas. We tested several models with nomenclatures indicated at the top. The 3 letters denote the use of upsampling process in feature extraction backbones, scaling detection, and indicator boxes, T for true and F for false. The model without an upsampling process in feature extraction and scaling detection achieved the best results, as scaling differences in this dataset were limited. However, when scaling detection was included, using the upsampling process proves more accurate. In the test for coordinate refinement, indicating compensation for feature points on fixed images, the RoTIR model demonstrated its self-refinement capability. Lastly, for the application of indicator boxes, referring to rectangular masks that roughly cover fish gills, it slightly improved the performance but was not significant. Since determining the indicator is labor-intensive, it is not necessary. We then check the rotation robustness of the RoTIR model. We assume the rotation angle of a pair of images to be alpha. Ideally, rotating the moving images by 90 degrees would increase the rotation angles accordingly. In practice, we expect the fluctuation for the detected angles, including moving image rotations, beta 1 to 4, to be minimal. Excitingly, all 45 test image pairs received promising results. Then, we recorded the rotation angles that received the best evaluation scores within each case. The chart shows that the recorded angles are evenly distributed in 9 equidistant angle ranges, proving the registration results are not influenced by input rotation differences. Thus, we can conclude the RoTIR model are rotation robust. Next, we tested the model without the rotation equivariant network for feature extraction, trained with the same configuration. Results shows that 35 out of 45 succeeded, but the evaluation result was significantly lower than those with rotation equivariant networks. The 10 field examples are shown here, with most exhibiting significant errors in rotation detection, and 6 showing serious translation errors. In conclusion, our work on the RoTIR model for zebrafish gill image registration successfully built a non-specific feature point detecting model trained on a synthetic dataset, meeting the requirements for the accurate registration and benefiting observation of zebrafish gills. However, there is room for improvement. Scaling detection capability was not thoroughly assessed in this work, and further analysis of other transformation factors, such as sharing or warping, could be involved. Specific point detection method could be introduced for more precise matching point selection to improve accuracy. Additionally, while this registration is for monomodal image registration, the more challenging task of multimodal image registration will be the next step. That concludes my presentation. Thank you for your attention.